everyone. So in this particular lecture, I'm going to be introducing you to some core topics in Chapter 10. Yay, Chapter 10, a new chapter. And in this particular lecture, I'm going to be starting with, right here, interparticle forces. Interparticle forces. So this is a topic that you did cover in Chem 10, and at least I'm hoping you covered it in Chem 10, and should be largely a review. In fact, most of what I am going to cover from Chapter 10 should be familiar. So yay for familiar topics. So let's jump in. Interparticle forces, what are they? Well, interparticle forces are the attractive forces that hold the particles of matter together. So the building blocks of matter, the particles of matter, depend on what type of substance you're working with. So for example, if we're dealing with a covalent compound, the particles are molecules. In ionic compounds, they're ions. In atomic elements, they're atoms. In molecular elements, they're molecules, so on and so forth. Blue. Okay, so let's start with ionic compounds. Well, when we're talking about the particles of matter in ionic compounds, we're talking about the cations and anions in those ionic compounds, which all get packed together in a three-dimensional crystal lattice. So let's write that here. Particles are the cations and anions packed into the three-dimensional crystal lattice, or lattices. And that's this picture I have over here of our cations and anions packed together in a crystal lattice, where the cations are the little green ones, and the anions are the bigger red ones. So that's just a little guide for us. Cations positive, anions negative in our crystal lattice. So what are the interparticle forces that exist between these cations and anions? Well, often they're called ion-ion forces. So I'm going to write that down over here. So our interparticle forces are ion-ion forces. Ion-ion forces. But we almost never use the term ion-ion forces, except maybe in this chapter. And that's because ion-ion forces are better known as, aka also known as, well, simply ionic bonds. So ionic bonds are, in fact, the interparticle forces in our ionic compounds. So over here in our structure, all of these lines represent our interparticle forces, which we could call ion-ion forces. But like I said, it's much easier to describe these ionic bonds, these ion-ion forces, as well. Like I said, they're just the ionic bonds themselves. Okay. Now, what do we know about ionic bonds? Well, we learned a lot about ionic bonds back in Chapter 8. That was the beginning of Chapter 8. And, for example, we know that these ionic bonds are incredibly strong, very, very strong. How strong? Well, if we're measuring in terms of, say, kilojoules per mole, they tend to range in strength from about 800 to 4,000 kilojoules per mole. And we found out back in Chapter 8, some of the factors that affect the strength of an ionic bond were the charges on the ions and the ion sizes. So you may want to take a look back over in your Chapter 8 notes. So let's write that over here, where you can again review what factors affect how strong or how less strong an ionic bond is. They're all very, very strong. And because they're so very strong, this is why ionic compounds always occur naturally in the solid state. You don't have naturally occurring ionic liquids or ionic gases. They're all solids because those very, very strong ionic bonds, those ion-ion forces, pull the cations and anions together very, very closely, very closely. And this is also why those particles are hard to separate, hard to melt ionic compounds, for example. Now, in this particular chapter, we're going to be focusing a lot more, not on the interparticle forces in ionic compounds, but instead on the interparticle forces in covalent compounds and in molecular elements. And so that's what we're going to look at next. In molecular covalent compounds and molecular elements, well, let me just scroll up a little bit here. Well, in these sorts of substances, the particles of matter are molecules. So let's note that first. Particles are molecules. And we call the interparticle forces between molecules, drum roll please, well, they're called intermolecular forces. So let's also note that here, that the interparticle forces, should be interparticle forces, are intermolecular forces. Abbreviated, of course, you should recognize this, I think, IMFs. Let's highlight that. Intermolecular forces, or IMFs for short. I do want to note that the term inter in intermolecular forces has a specific meaning. It means between. Between. In other words, intermolecular forces are the forces, the attractive forces between molecules that keeps them all grouped together. So, for example, let's suppose let's just draw some sample molecules. So here we go. Let's draw a few molecules. One molecule. Let's draw a second one here. Two molecules. And let's draw a third one here. Three molecules. Let's suppose we have a collection of these three molecules here. Now, each molecule is being held together by bonds. In this case, since I drew little diatomic molecules, this blue line, of course, represents the single bond. There's a covalent bond that is holding the atoms together. But what's keeping the molecules themselves together? So each individual molecule is attracted to the next molecule and the next molecule. And these attractions are often shown as a little dashed line. I'm going to show it a little dashed line in yellow. So this molecule is attracted to this one, and this one with this one, and this one with this one. They're all attracted to each other. And these little yellow dashed lines here represent our intermolecular forces. They're the forces between the molecules that's keeping them all together. Now, in contrast, I should note that the blue line between our atoms, the blue line, of course, represents a covalent bond. So that's a covalent bond. And we never want to mix up bonds, covalent bonds, I should say, with intermolecular forces. Those are two distinct things. The covalent bond holds the atoms together in the molecule. And sometimes we can think of a covalent bond as an intramolecular force. Intramolecular force, where the term intra means within. So a covalent bond is a force within the molecule, which holds the atoms together. IMFs, intermolecular forces, occur between the molecules, holding groups of molecules together. Now, I should note here, it even says note, that intermolecular forces are much weaker than covalent bonds. Now, covalent bonds themselves are weaker than ionic bonds. Ionic bonds are very, very strong. Covalent bonds, well, they're pretty strong. They're just not as strong. Covalent bonds tend to range, depending on whether it's a single or a double or a triple bond, tend to range in strength from about 200 up to about 1200 kilojoules per mole. But intermolecular forces are considerably weaker than the covalent bonds. They tend to range from about 0.05 up to about 40 kilojoules per mole. And we're going to be talking a lot more about the strength of the intermolecular forces at the end of this particular lecture. Now, why are we so interested in learning about intermolecular forces? Well, it turns out intermolecular forces have a huge effect on properties of covalent substances. For one thing, they influence the states of molecular elements and compounds. So whether you find a compound, a covalent compound, or a molecular element in the solid or liquid or gas state, well, it's actually due to those IMFs. And IMFs also influence the properties of these substances, properties such as melting point or boiling point, or over here I have liquid viscosity, etc. We're also going to be looking at these things in later lectures in chapter 10. Now, what we are going to focus on are the types of intermolecular forces that occur between molecules. As it turns out, there's several types, and we're going to see what those types are and when they show up. So, there are three types of intermolecular forces that occur between pure substances. So we're focusing on IMFs in pure substances. And the first type are called dipole-dipole intermolecular forces, which sometimes I'm just going to abbreviate with DD for dipole-dipole. And as it turns out, these are the attractive intermolecular forces that are found between polar covalent molecules. So if we've decided that we're dealing with a polar substance, dipole-dipole intermolecular forces are what we're going to find holding those molecules together. Now, how do they work? Well, we know that a polar molecule has a non-symmetric electron distribution throughout it, meaning that one end of the molecule has a slight negative charge and the other end has a slight positive charge. And so what happens is that these dipole-dipole forces come about when the negative end of one polar molecule is then attracted to the positive end of the polar molecule beside it. And I'm using as an example here HCl. Now, these HCl molecules aren't shown as complete Lewis structures. I'm going to go ahead and complete one of these molecules. Let's complete the molecule on the left. I'm going to start by putting in the lone pairs. Each of these chlorines does have an octet. So if we put in our three lone pairs, it's good to go. I'm not going to show this on the other HCl's, just this one here. And, well, this is a polar molecule. So this is a polar molecule. What makes it polar? Well, the electrons in this bond are being pulled towards the more electronegative chlorine. So they're being pulled in this direction. And as a result of this, the electron distribution in this molecule is going to be asymmetric. There are going to be more electrons on the chlorine side than the hydrogen side. And sometimes this is shown in a cloud diagram by showing a slightly asymmetric cloud of electrons, with the asymmetry being bigger towards the more electronegative element. We sometimes show this also using colors. And in this case, I'm going to show that the chlorine side of this molecule, all right, is where the electrons are pulled towards. And of course, that's going to make this end of the molecule permanently negative and the hydrogen end permanently positive. Now, this is also going to be the case for the other two HCl molecules that I've drawn here. So this one is going to be a polar molecule. This one here is going to be a polar molecule with a non-symmetrical distribution of electrons being pulled preferentially towards our chlorine side of the molecule, and the chlorines ending up with a permanently slight negative charge, and the hydrogens with a slight positive charge. Now, the dipole-dipole interactions between these molecules is coming about because the negative end on one molecule, over here, the chlorine, is being attracted to the positive end, the hydrogen end, of the adjacent molecule. Same thing over here, chlorine end of one attracted to the hydrogen end of the other. And so what does this represent here? Well, this represents our dipole-dipole intermolecular forces, is what this is representing here and here, that are keeping these molecules together. So that's the first type of intermolecular force. I'm going to scroll to the next page for us to take a look at the other two types. And the second type we have here, called hydrogen bonding intermolecular forces, is in many ways very similar to dipole-dipole forces. I'm going to abbreviate hydrogen bonding as HB. I bet you could have guessed that. So when does hydrogen bonding take place, and how does it take place? Well, first of all, it is a much stronger type of, well, it's a type of dipole-dipole interaction. But what makes it a bit different is that it occurs between highly polar covalent molecules. I like to call these molecules superpolar molecules. Superpolar molecules. Now, what makes them superpolar is that they contain at least one really, really polar bond. And these really polar bonds typically occur when a hydrogen atom is directly bonded to either a fluorine or oxygen or a nitrogen atom. Now, hydrogen atoms have a very low electronegativity value, but fluorine, oxygen, and nitrogen have very high electronegativities. And so delta chi, the difference in electronegativity, is going to be really, really large for either one of those bonds. And that gives us that really highly polar bond, making our polar molecule not just polar, but superpolar. So just to make sure that you understand what I mean by this over here, what I mean is that our polar molecule has got to have either a hydrogen-fluorine bond or a hydrogen-oxygen bond or a hydrogen-nitrogen bond to be considered superpolar and have hydrogen bonding intermolecular forces. I'm going to write that over here. So the polar molecule must contain a fluorine hydrogen bond or an oxygen hydrogen bond or a nitrogen hydrogen bond in order for that molecule to be superpolar and for the type of IMFs to be hydrogen bonding IMFs. So the example I'm using to illustrate that here is with our good old friend water molecules. So again, these are Lewis structures that are not complete. To complete the Lewis structure, I'll just do that for the left-hand water molecule. We're going to put two lone pairs on this rather naked-looking oxygen atom. I'm not going to complete the other Lewis structures. Now, the bonds in this molecule are polar. So this bond is a polar bond where the bond electrons are pulled towards oxygen. And this bond is a polar bond where the electrons are being pulled strongly towards the oxygen. And the molecule is overall polar. Why? Because it's a bent molecule. Being bent, the bond polarities do not cancel. So we know it's a polar molecule. All right. And what makes it a superpolar molecule is the presence of those OH bonds. So I'm going to write that here. Let's fix that. Oh, come on, I'm not doing a very good job of that, am I? Superpolar due to the OH bonds in water. Okay, well, what does that mean? Well, that means once again that there's going to be an asymmetrical distribution of electrons in this molecule. The electrons in this molecule are going to be heavily pulled towards the oxygen end of the molecule in all of these water molecules that I'm showing here. Very much distorted. And let's just get a blue pen over here. So more electrons pulled on this side towards the oxygen end of the molecule. And of course, this is going to give the oxygen end of the molecule a permanent negative charge, or slight negative charge, and the hydrogens are going to get permanent positive charges, slight positive charges. These are deltas, little lowercase deltas that I'm drawing with the negatives and positives. So what happens now? Well, hydrogen bonding IMFs work just like dipole-dipole IMFs. They're just stronger. And so once again, we're going to see that whoops, and I made a little mistake, and nobody yelled at me because, well, you can't yell at me for making a mistake when I do it in a video. This obviously is a negative right here. So yes, this negative end here is going to be attracted to the positive hydrogen end on the adjacent molecule, and same thing is going on right here. Negative end, the oxygen end on one molecule attracted to the hydrogen end on an adjacent molecule. And over here, well, these intermolecular forces are hydrogen bonding intermolecular forces. Okay, not so bad so far. Well, the third type of intermolecular force is called London dispersion. London dispersion IMFs are what's next, right here. And well, we're going to abbreviate London dispersion forces using an L and a D, London dispersion intermolecular forces. So under what conditions do we find London dispersion forces? Well, as it turns out, we find them in all covalent molecules. So I'm going to highlight this. London dispersion forces occur in all covalent molecules. However, they are the only attractive forces found between non-polar covalent molecules. Okay, so let's start with the first thing I highlighted, that London dispersion forces occur in all covalent molecular substances. That means in the preceding example, which was water, which I said the IMFs were hydrogen bonding IMFs. Well, that's true. The IMFs here are predominantly hydrogen bonding intermolecular forces, but we also have London dispersion intermolecular forces occurring between our water molecules. They're not as strong, they are not as dominant as the hydrogen bonding intermolecular forces, but they are present there as well. And if I scroll back to my earlier example of HCl, there we go, there's HCl, where I said that the IMFs are dipole-dipole IMFs. Well, that's true. And they are the dominant type of IMF present, but London dispersion intermolecular forces are also occurring between these molecules. Now, London dispersion intermolecular forces are the only type of attractive force that we will find between nonpolar covalent molecules. And as an example, we're going to take a look at diatomic chlorine, which is a molecular element. So I'm going to complete the Lewis structure of the molecule to the left by putting in all of the lone pairs. Again, I'm not going to complete the other Lewis structures. And this, of course, is a classic nonpolar molecule. It's a nonpolar molecule because both chlorine atoms have the same electronegativity and the bond electrons are being shared equally on average. And so we might imagine that the electron distribution in this molecule is perfectly symmetrical. Let's use a different color here. Perfectly symmetrical on all sides. Over here, same thing. Electron distribution, perfectly symmetrical or even is another word we could use for that. Over here, perfectly symmetrical electron distribution. I'm doing my best here to make it look symmetrical. And as it turns out, well, once again, these molecules are in fact attracted to each other. So again, I'm going to put in my little attraction lines between the molecules. And well, these represent, again, the intermolecular forces, which in the case of our nonpolar substances has to be London dispersion. So we have London dispersion IMFs holding our nonpolar molecules together. And I should note that these are the only intermolecular forces that we find holding together the molecules of nonpolar substances. Now, it was really easy to see how attractions occurred for dipole-dipole and hydrogen bonding intermolecular forces. But now our question is, well, what is causing the attraction of London dispersion intermolecular forces? Why are they attracted to each other? Well, it turns out that, as you know, nonpolar molecules do have this symmetrical distribution of electrons on average. So I'm going to start by just drawing my little green cloud. We could think of this as a cloud of electrons in their molecular orbitals. And yes, they could be considered to be our perfectly symmetrical distribution of electrons. Here, let's just clean this up a little bit. There we go. And maybe this one up a little bit. It's hard to control my stylus here. But this is only true that they have a symmetrical distribution of electrons on average over time. So let's remember that the electrons in a molecule are not stationary. These electrons are within their molecular orbitals. And within a molecular orbital, an electron could be anywhere within a molecular orbital. So it is possible that at a given instant in time, those electrons could just randomly move a little bit to the left, or maybe they could randomly move a little bit to the right. In other words, for that one instant in time, what happens is that the electrons randomly shift into a non-symmetrical arrangement. And if that happens, that molecule, which was nonpolar before, acquires what is called an instantaneous dipole moment and becomes very slightly polar. So for example, let's take this chlorine molecule. This chlorine molecule's electrons may randomly shift a little bit to the left. So if they shift a little bit to the left, well, now we have our asymmetric distribution of electrons. There we go. Let's try drawing this. Okay, that's not great, but not horrible. Let's see if I can clean it up. Okay, that's a little bit better. So now we have an asymmetric distribution, but it's only for that instant in time. So here we go. Let's get a green arrow here. So what's gone on over here is there's been a little bit of a shift of electrons in this direction, for that one instant in time. And for that instant, we have a higher electron density on this side of the molecule, which makes this molecule polar for just an instant. And that gives this chlorine atom on this side a slight negative and this one a slight positive. Okay, now this happens all the time. And I'm just going to make my other chlorine the same way it was before. So this chlorine has undergone no change. At least it's undergone no change up until this point of time. So I'm going to underline some important words here. Over here, we get this thing called an instantaneous dipole moment for our left side chlorine molecule. Now, our second chlorine molecule is going to react to our first chlorine molecule. Whoops, I didn't mean to do that. So because the chlorine atom that is closest to molecule number 2 is now slightly positive, well, the electrons in this cloud are going to be attracted to that slight positive charge, which is going to cause these electrons in the cloud over here to want to move to the left, because they want to be nearer to that positive charge. And this is exactly what happens. We say that the molecule that has an instantaneous dipole moment then induces a dipole moment in the adjacent molecules. So here's how we can think of it. Here's my first molecule, which has its instantaneous dipole moment. And let's just sort of, oops, I didn't want to do that. Let's try this again. With all the colors, it's getting to be a little fun here. Okay, here we go. So this one with our little positive end and our negative end for an instant. Well, like I said, it's going to be promoting the electrons in our second molecule. This should be a positive here. The electrons in the second molecule are also going to want to move left to get closer to the positive charge, right? And when they do that, we get a distortion in their electron cloud. So we get a non-symmetric distribution over here in response to the first molecule. And so once again, we get more electrons on this side because they're trying to rush over to be close to that positive end. And of course, this gives this a negative end and this a positive end. And so because we have caused these very tiny dipole moments, well, what happens is that the molecules can finally be attracted to each other. Positive end to negative end, where these attractions are our London dispersion interactions. intermolecular forces. And so again, I'm going to just underline something key over here. This in turn induces a dipole moment. That's what's important over here in our adjacent molecules. So over here, this molecule ended up with what's called an instantaneous dipole. And once it got its instantaneous dipole entirely by random motions of electrons, all right, it caused the second molecule to get what's called an induced dipole. Now, I should note that these dipoles, instantaneous and dipole, are very, very slight dipole moments. And not only they're very slight, they're constantly shifting. So remember, the first molecule that got this instantaneous dipole moment over here, it was just random that the electrons shifted left. So they could just as easily have shifted to the right. And in fact, they're constantly shifting about. So I'm going to write that down here, that these slight dipole moments constantly shift about. Okay, so these are our three major types of intermolecular forces found in, again, pure substances that are composed of molecules. Well, now let's do an example. Example number 1 for our in-class examples for Chapter 10. And our example simply asks us to identify the types of intermolecular forces that occur in the substances shown below. So a key for you to identify the right IMFs is to know whether a substance is polar or nonpolar. Now this is going to bring us back to Chapter 8. In Chapter 8, to know if a substance is polar or nonpolar, you had to be able to draw the Lewis structures correctly. You also had to get the shape correct, because if the Lewis structures and the shape weren't right, you could not possibly know whether the substance is polar or not. Now, in the case of this example, I'm already giving you the correct Lewis structures, and I'm also showing the Lewis structures in perspective so that you can see their shapes very clearly. But this is key. You got to know the shapes of these molecules, or you cannot get whether they're polar, and then you can't get whether they have a particular type of IMF or not. So our first question is, given these substances, are they polar or nonpolar? So let's start there. So let's take a look. We have OF2. The OF bonds are definitely polar, and these bond polarities won't cancel out because it's a bent molecule. So I'm going to note that this is a polar molecule. Over here we have NH3, which is ammonia, and ammonia also has polar bonds, which again don't cancel out, so this is also a polar molecule. Next we have carbon dioxide, CO2, which is perfectly linear. The carbon-oxygen bonds are polar, but the bond polarities cancel out because it's linear, making this a non-polar molecule. The fourth molecule I have over here is called formaldehyde. And formaldehyde is in a trigonal planar arrangement with the 2 hydrogens and 1 oxygen. And it's clearly going to be a polar molecule because the carbon-oxygen bond is way more polar than the carbon-hydrogen bonds. So bond polarities can't possibly cancel out. This is a polar molecule. My fifth molecule in the next line over here is methanol. And methanol is definitely a polar molecule, a most non-symmetric molecule, followed by SF6, sulfur hexafluoride, where all the sulfurs are arranged in an octahedral arrangement, causing all of the bond polarities to cancel out. This is a non-polar molecule. And bringing up the rear with our examples, BCl3, which is in a T shape, and as such, the bond polarities do not cancel out, and it is a polar molecule. So that's where we start. Simply decide polar or nonpolar. Now, if it's a nonpolar molecule, we know automatically that the only intermolecular forces are London dispersion forces. So over here, I'm going to write London dispersion, LD for London dispersion. Now, we need to be a little bit more careful if we've decided a molecule is polar. And the question we need to ask, is it regular polar or is it superpolar? Now, for a molecule to be superpolar, we need to see in that molecule either a fluorine hydrogen or an oxygen hydrogen or a nitrogen hydrogen bond. So our first polar molecule, OF2, is regular polar. But our second molecule, ammonia, we can clearly see fluorine hydrogen bonds, which makes this superpolar. At the end, we have formaldehyde, and again, I'm not seeing oxygen attached to hydrogen. There's oxygen and there's hydrogen, but they're not bonded together. So that's going to be regular polar. But over here in methanol, we've got a very prominent oxygen atom bonded to a hydrogen atom, which is going to make this superpolar. And well, we neither have oxygens or hydrogens or fluorines or nitrogens in the last molecule, and so it's got regular polar. Now, if it's a regular polar molecule, this means that the IMFs are both dipole-dipole and London dispersion, where dipole-dipole is the predominant type of intermolecular force. So I'm going to write that over here, dipole-dipole and London dispersion, dipole-dipole being more important. And same thing over here, dipole-dipole, London dispersion with dipole-dipole being more important. And in the superpolar substances, in this case ammonia and methanol, we are going to have hydrogen bonding and London dispersion. Hydrogen bonding and London dispersion, where hydrogen bonding dominates. Okay, not so hard. But again, note that our understanding of how to draw Lewis structures, getting their shape, getting polarity right is rather critical. Now, I do want to talk about one more thing before I end off this little lecture here, and that is about the relative strength of intermolecular forces. So as it turns out, intermolecular forces actually range quite considerably in how strong they are. Turns out that hydrogen bonding intermolecular forces range in strength from roughly about 10 kilojoules per mole up to 40 kilojoules per mole. Dipole-dipole intermolecular forces range from about 5 up to 25 kilojoules per mole in strength, while London dispersion forces range from as low as 0.05 all the way up to 40 kilojoules per mole. Now, I'm pointing this out because sometimes students will tell me, oh, hydrogen bonding is always strongest, and that's not true. So because hydrogen bonding has a range of strengths, if the hydrogen bonding strength is 10 in one particular substance, but the London dispersion forces in another substance are 40, well, that's not going to be true in that case. In that case, the London dispersion forces would be stronger. So we have to appreciate that there's a range of strength. However, what we do find out is if we compare molecules with similar molar masses, in other words, they almost have identical molar masses. Not necessarily identical, maybe just a couple of grams per mole different, but as long as they're very close in values, under these conditions, what we do see is that London dispersion IMFs tend to be the weakest, followed by dipole-dipole, followed by hydrogen bonding, which tends to be the strongest, but only under this very limited set of conditions. So I'm going to write that down here. London dispersion IMFs less than dipole-dipole IMFs less than hydrogen bonding IMFs, but only if this condition is met. So let's just note that what we're seeing here is that, oh, that's a terrible straight line. Let's see if I can't try that one more time. Not much better, but I'm doing my best. So from one end to another, what we're seeing here is IMF strength is increasing. So if two molecules have almost identical molar masses, but one has hydrogen bonding IMFs and another has dipole-dipole IMFs, we would go with the one with hydrogen bonding IMFs as the one with the stronger IMFs. Now, there's a caveat to this rule, and that caveat applies to hydrocarbons. What's a hydrocarbon? It's a molecule composed of just carbon and hydrogen, which makes it a covalent substance composed of molecules. So hydrocarbons with similar molar masses tend to have stronger IMFs if they have less branching. So similar molar masses, stronger IMFs if they have less branching. Now, this is not going to be a really important thing for you to focus on now, but someday you're going to get to organic chemistry, and organic chemistry is all about hydrocarbons, and this little rule might be handy to pull out of your brain when you're in organic chemistry later on. But let me give you an example to explain what I mean by this. I'm going to compare two hydrocarbons with identical molar masses. One is called butane. Butane, I'm going to write out its Lewis structure. It has 4 carbons. 1, 2, 3, 4. And to the terminal carbons, we have 3 hydrogens attached. And to the interior carbons, we have 2 hydrogens attached. So let's just put in some hydrogens. So this here is butane. Now, an isomer of butane, which has the exact same number of carbons and hydrogens and therefore has the same molar mass, is called isobutane. Isobutane has a chain of that's a hydrogen here, of 1, 2, 3 carbons. And the 4th carbon is hanging off the middle carbon here. And well, this carbon has 3 hydrogens, 1, 2, 3. This carbon has 1 hydrogen. This one over here has 3 hydrogens. And this carbon down here has 3 hydrogens as well. Okay. And when we compare these two molecules, which I'm going to note have the same molar mass, what we find out is that the first molecule has stronger IMFs and the second has weaker IMFs. And this is because the second one has more branching. So weaker IMFs, more branching in our hydrocarbon. So well, why would the hydrocarbon with more branching have weaker IMFs? Well, obviously isobutane is a more compact molecule. And more compact molecules are going to have less what we call surface area interactions with other molecules. And because they have less surface area interactions with other isobutane molecules, they're going to end up with weaker IMFs because of minimal interactions and minimal attractions. So I'm going to write that down. So it's more compact. So we have less surface area interactions with other molecules. So weaker attractions. There we go. Again, not so important for chapter 10, but this little bit of knowledge could really save you in an organic chemistry class, for example. Now, what is really important for you to know, much more so than this little sidebar about hydrocarbons, is this last little special note. We found out that for molecules, back up here, with similar molar masses, that London dispersion forces tend to be weaker, hydrogen bonding intermolecular forces tended to be stronger. So weaker at this end, stronger at this end. But what happens if our molecules have different molar masses? Well, as it turns out, as molar mass increases, IMFs tend to get stronger. And this is especially true for London dispersion forces. It's true for all types of intermolecular forces, but very much the case for London dispersion forces. And so again, why is this the case? Why does an increase in molar mass lead to stronger IMFs, in particular stronger London dispersion IMFs? So I'm going to say why over here, and let's answer that question. Well, the answer is simple. Molecules with higher molar masses have more electrons. Okay, there's a correlation. So molecules with higher molar masses have more electrons. What's more electrons have to do with anything? Well, more electrons makes a molecule more polarizable. I'm going to write that word down in capitals, polarizable. So what does that mean? Molecules are more polarizable if they have higher molar masses with more electrons. Well, polarizability has to do with how easy it is for the electrons to shift into non-symmetric distributions. In other words, a molecule that is more polarizable because it has more electrons is going to more easily obtain an instantaneous dipole moment. And that's because the probability of more electrons shifting into non-symmetric distributions is higher than the probability of less electrons shifting into a non-symmetric distribution. So I'm just going to note that this means that it's now going to be easier for our molecules to obtain an instantaneous dipole. And if that's the case, well, the IMFs will definitely end up getting stronger. There we go. Instantaneous, that's a long word, dipole. And so IMF strength goes up, because we can't have any IMFs at all between especially nonpolar molecules if we don't get those instantaneous dipoles. So if we improve our ability to get instantaneous dipoles, the strength of our intermolecular forces will therefore have to increase. So this is a rather important point. So I'm going to put little stars around this point as well. Okay, so we're done with this lecture. Coming up next, we're going to be talking about how intermolecular forces affect the states of matter and how they undergo changes of state. Okay, so until then, take care everyone, and I'll be talking to you really soon. Bye now.